Okay, PLC program for MasterSlave sync position absolute. I'm going to try and cover everything in this. I hope I don't brush by some things that aren't obvious to people, but I'll do my best. I already have a PLC project, and because of the extensive work I've done on this, I'm not going to start from a brand new project and do everything from scratch. I'm going to show you as I go along how I arrived at where I am. Okay, so the first thing I want to discuss is the process data. Okay, if I go to the user manual, where did I get the user manual? I think we've discussed this already, but I'll go to the website here, and if I take this CMMT and I do a search for CMMT, you will see here that as of today, this is the 12th of the 8th of December 2022. This product is being discontinued, and that's because the CMMT series, which used to have this EP or PN or a EC for EtherCAT, they were all individual controllers with one field bus, and now all the Ethernet-based real-time controllers are going to what they call a multi-protocol. So you basically purchase this instead, and you have one controller that's capable of all the Ethernet real-time ports. So Profinet, EtherCAT, EthIP, and Modbus. So anyway, so we get to this, we arrive here, and we realize that, hey, we're in a problem here, but we can still go to the search and type in the product right here and come up with the results shown here. So if you want to go right to the multi-protocol, you could click on show details and close this, and this will get you right here, because this is where I clicked. There's the multi-protocol right here. So I'm going to leave this page open. I'm going to leave this page open, and the first thing we need to look at when it comes to process data is in the PLC, we need to set up connections between the PLC and the CMMT controllers. And this little section in the user manual does a nice job of explaining instances and how many bytes of data there is. It talks about the extended process data, how many bytes of data there is there. Then it starts talking about what that process data is. If you go a little further into the manual here, and we'll see here that Telegram 111, which if you remember in the setup, we chose Telegram 111. And it's under this one on the multi-protocol. Sorry, it is profile Telegram under Profi Drive, because it's Profi Drive over EthIP, and we've chose 111. Okay, and then we have all these little bits and bytes underneath this one telegram. If we go further into that, I've created my own little IO map after reading many manuals, and these are all the individual bits and bytes of the process data. Won't get that deep into this right now. That's not the topic we're discussing. But basically, go back to the PLC program here. Go back to the internet. When we type in our drive and we go to downloads, go to software on the left, then we'll realize here that we can find the EthIP EDS files. Okay, so you can click on this, tells you what controllers it's valid for, and then you download the EDS file. When you have downloaded it, then you can do the EDS installation tool, and then follow the prompts, install the EDS file, next, register. Then you pick the file and so forth. Then it adds to the database. I'm going to cancel that, and at that point you can right click and say new module, on your Ethernet bus. So this is a PLC project. I've already added my PLC, configured it. It's an L30 ERM. It's a version 20 PLC program on purpose. It's as old as it can get so that everything is compatible moving forward. And at this point, if I type in CMMT, because I have registered the EDS file already, I can select this. And at that point, I would say create. Okay? So, I'm not going to do that because, as I said, I already have done that. And what I have done here, if I said create, it would add this first one here. So I'm going to double click it to open. And it prompts you for these things. So it gives you, tells you what do you want to call it. I'm calling this the master. You give it an IP address, which is the connection to. So I'm essentially saying connect to the master. Real-time port of 185. And if I go back, there's the 185. And what we're saying here is, this is the definition here. This is where we say, okay, the process data, it will be already configured, this first row right here, as process data, int format, 12 ints, which is 24 bytes. We go back to the user manual. There's my 24 bytes of process data in and out. Okay? Go back to the PLC here. This second thing here is the extended process data. Okay? Forgive the drop-down menu. They're not the best because it's a Rockwell issue, not a Festo issue or EDS file. It's a Rockwell. And we configure the process data so that it is exclusively owned, and we give it a revision number or whatnot to match that of the hardware, and we say okay, change, and it's done. At that point, you can expand these drop downs here so we know we have drive profile exclusive owner. That's one connection, unicast, and then we have the extended process data, 1 millisecond requested packet interval, unicast. And that's all there is to it. At that point, we have a connection. And the name that's been created here will end up in your controller tags. So if you go to controller tags, anything that's grayed out, that's the name. So these are my process data. I know it's not very clear, but that's just the way of the world in this old PLC program here. And so on and so forth. And we did the same thing for the slave. The only difference between the slave and the master is the IP address is 224, and the name is different. Okay? So now that we have the process data and we have the extended process data, now we want to be able to use it in the program. And as I showed you here, the process data itself is quite extensive, bits and bytes, and you may not want to really know everything about this and get into detail. This is a Profi drive Siemens Telegram 111, and this is being communicated over the EthIP bus. And if we go to our PLC program, we want to use that data in a more user-friendly way. And in order to do that, Festo has created some function blocks for Rockwell, just like they have for other controllers like Siemens and Omron and things like that. So if we're on the website here and we're selecting our multi-protocol or our drive here, whichever we prefer, go to the software under downloads, and you will scroll until you find function blocks Codesys, function blocks Rockwell. So version 2.4, function blocks Rockwell. You'll download this here, and talks about some changes that have happened. Okay, so this library by itself, this library will have a user manual itself, and you'll be able to follow and get to a point where you've done everything here step by step in the user manual, and then it basically shows you how to import these add-on instructions. Okay, what are these add-on instructions used for? Okay, the add-on instructions, point-to-point drives Festo EIP and extended process data. Well, in the previous configuration here, we set up parameters to be transferred over the extended process data. That is a comparison match to this add-on instruction. What this is used for is to gather the data, either send or receive, and then the process data comes through on this add-on instruction here. So if I minimize that and expand my project here, I'm just going to close my tags. I have added some subroutines here to my main program. The main program is scanned all the time, and I have two routines for each controller. One has the AOI, I call it, and that is for the process data. So if I double click on here for the master, scroll a little bit here, you'll see here that this point-to-point drives Festo EIP, which is this person right here, this AOI or add-on instruction or function block, whichever way you want to look at it. This is an instance of that block, and in that guide that we have downloaded right here, the guide shows you how to set this all up, link it to the process data. Okay, so if I right click, go to monitor, this will take me right to the tag, and again, it's not the best tag. I can zoom in here. It's basically linking to this master data tag right here. That's for the input. That's what the I stands for, and then there'll be an output. Again, monitor. I zoom in here. There's my output data. And then this right here is connection faulted. So that's discussing these connections right here. Again, that's explained in detail in that user manual for the add-on instructions library. And this right here, I have some standard code that I use to monitor status of Ethernet connections, and as well the connection itself comes through here. So this connection fault is part of the tag when you have an EDS file. There's a connection faulted status for each connection. You know, the I2 is the extended process data connection, and there's the same thing for this as there was for the other one. So the I2 has one, and the I1. So going back to the code here, all of these bits and bytes here are all explained in the user manual, and this is the interface at this point that replaces all these bits and bytes. Okay, it's quite a nice package, and this is what you should be using to control running the drive, positioning it, going and so forth. I've added some text here, a meaning, because the mode pause here, depending on the mode pause, it means a bunch of different things. So we have this set up right now for the process data, and then if we go to the EPD AOI, then we have the extended process data. And again, if you read the manual, it talks about the fact that there's objects that are written here, and the objects will get mapped. As we said, we have to set up the fact that this right here is a floating point 32, this one here is a Syn64, this is a Syn64. those values will mean something in the code, and we have to set it up. This is a EPD input and output configuration here, and we need to set up these objects so that they are of the correct data type, and then the data will come through accordingly. All right. What I do is, traditionally, if I monitor the tag here and expand this, I like to label the raw data so that it matches that of what I have in the code here. So 4643, 128, 4643, 128, and 116011. So I show how much space it occupies and so forth. And keep in mind that this extended process data add-on instruction deals with certain data types really well, and then other data types not so well. Specifically, long integer is a problem for both the older processors and for this particular add-on instruction. So in some circumstances, I use the add-on instruction, for example, this floating point coming through, and then other ones I simply take the raw data and do my own conversions, because all this add-on instruction does is convert the raw data into these objects here, and then the user can use the objects throughout the code. So I've got a little rung of data right here, which I don't necessarily need to have, but it's just there for viewing purpose. Object 0, as similar to the raw data, is floating point 32. It's P4643, which is the encoder monitoring window. The object 1 is a long integer actual position encoder, and then object 3 is a long integer. Well, I don't use these objects throughout the code because the long integer needs to be converted properly. Down below here, I take this object right here and I convert this to millimeters so that it's a match. This is my connection fault, and at the bottom of this routine here, this is me taking the raw data and converting it to a long integer. So at this point, I'm taking an array of 8 cents and converting them to one long integer so that I have a meaningful data. And then these data types, or these tags, are being used throughout the code. Okay, and the PNU represents encoder 1, X2 port actual position, and this one right here is PNU 02940, the related parameter PNU, and this is encoder 2, which is the X3 port, and I use that for comparing and doing a bunch of math throughout the code. And that's pretty much how the extended process data works and the process data works. So now that we have all that arranged, you have to understand that the rest of my code here will be using those add-on instructions to send and receive data throughout the code. For example, if I go to my common code for the master, we'll see here that I have a master underscore fb.axis error, and then based upon all that information there, master underscore fb.cancel traversing. Well, those bits all exist on the AOI right here. So there's the cancel traversing, there's the name of the block. If I go to monitor this tag, we'll see here, if I expand this, that all these tags exist right here. So it's like there's the cancel traversing, other ones that are obvious, those are all there and defined within the add-on instruction. Okay, and let's look at this. So Looking at my code, we'll see here that I have this one standalone bit. Okay, the standalone bit, it allows my code to stop scanning code and only allow the user to play with the add-on instruction. Okay, it's also over here. So if at any point in time I want to debug something, I can basically toggle this so when this is off, the code is working, and then when this is turned on, then the user controls this AOI. So I can literally come into here, put a 1 here, and it should start to respond, if I'm online, of course, and use this. So that if I ever want to try something out, I can go back and forth. So that's what that bit's for. Additionally, in this code here, if I zoom out a little bit here, it's a little hard to see, but basically this rung right here enables the axis. The rung 3 here is a fault reset because it acknowledges the errors on the axis. This bit right here is a programming bit, so I can either right click and say toggle the bit off and on, or I can control T to toggle this off and on, so that if I want to manually do that, it will go off and on. This create drive ready is used to simulate certain things. You'll see here that the slave also has a common control routine. So let me just close them all for a second here and then come back in. Master common control, slave common control. You'll see here that the big difference between the two, other than some sequence bits, are the fact that the synchronization complete is in line with enabling the master. So the order of operations for gearing in and syncing the axis together is to clear all the faults and have the slave synchronized to the master. And once that's complete, only then do I allow the function block or the master to be enabled. If I look at my code further here, I have some pre-move safety conditions. Okay, so from a master standpoint, I have the ability, or the code will execute moves back and forth, just reciprocating the axis back and forth. So I have set up moves. I'm not using move number 1, but execute move number 2. Or I set up, mode, accel, decel, velocity, and a target. So if you're going to be using this code and your axis is not 175 millimeters long like mine, you might want to change these target values here. You would just basically come in here and modify this value to whatever it wants to be, and then you're changing it. So this routine here, I'm basically telling it to go to 170, then 65 millimeters, then 25 millimeters, then 10 millimeters, and then back to 0. And then the sequence will start over. So these are the setup of the moves. This right here is the sequence. Sequence is pretty straightforward. It's a little stepper. As code executes, each step will go on. When that action is done and these feedback bits are proven, then the next part of the sequence takes place, and it will continue down the road here. This is where we stopped, for example, when I was online, and so this would be a move start. When the move is complete from the other part of the code over here, then the move 2 is complete, and then the next step will be move 3 start. So this basically just steps through and so on and so forth. It just cycles the master back and forth. Of course, the slave is going to be synced to the master, and both axes will be moving synchronized or parallel to each other at the same time. Okay, I'll talk more about this one when I'm all online. Sequence recovery, that's not something you really need to understand. It's just so that when I have an e-stop or something and simulate this by dropping one of these bits, that if a move was taking place and I give the e-stop back and start the sequence over, the sequence will start off where it left off. Then we have some things related to our sequence for syncing. Okay, this right here talks about everything to do with the absolute position of port X2. Okay, gives you the details on everything. This is all from the user manuals, and I use this value to compare values later. This one right here is the X3 actual position. Again, there's my value here. I don't need this code here, it's just for my own sanity, understanding stuff. Encoder difference monitoring. Okay, this right here is some mathematics so that at the beginning of any sequence for synchronization, I'm comparing the variety of encoder positions to each other. So basically, if I'm out of sync and the gear in is not active anymore, the first thing is I'm going to do is I'm going to come through my master here and I'm going to look at this position and I'm going to compare it to this position. And if I'm not synchronized to each other, then I need to set a master position of this X3 port. Again, I look at the absolute position of the master and I go to the slave and I compare that to the position right here on the X3 port. And if that's not equal, then we need to synchronize. And so on and so forth. That's what all this math does, and I set a bit based upon the set master position required. Over here I'm doing some compare values, which is all explained in detail. It's not very often that you'll actually need to come into here and look at this. But it's quite detailed. Then I have this master PNU 10,002 W long end gear position. So what this does here, if you go to the user manual, there are methods. So there's a whole section here called Device Services and Methods. Read it. It's a real good understanding here in the user manual. But basically, in order to set the master position, there's these 4 PNUs, and there's a procedure for doing that. So in my code, I have a full procedure. Again, it's a little stepper, and I use this stepper to go through, and if I scroll down, keep going here, get to a point here where there's a complete, but basically I have these explicit message instructions that are reading and writing to the PNUs as described in that method, and depending on the sequence, I will come through here and I will write a new value right here. So this value right here is quite convoluted. If I zoom out, it's quite deep. But this message right here takes a value, converts it from a long integer to an array of 8 bytes, and then it writes that value to the controller. And in doing so, it's changing either this absolute position here on the slave or the same on the master. And that's where we're going to synchronize the encoders and be or have no encoder offset at all. So with that, said, we have the exact same situation here for the slave. We have the actual position of x2, x3. We have a comparison value there, and then we have a gear in position for the slave. How is that all controlled? This sync sequence right here. Okay. If I double click on this, or close the other ones here, hang on. If I go back into here, and close this for 1 second, just back step a little bit, you'll see here that this gear in position, the method, the whole sequence of what I'm doing here is explained in detail right here in this method sequence. Okay. This talks about the device services in the user manual, and then this talks about the method sequence that I'm executing. So if you're really interested in how this works, and you don't just feel like it's just going to do its job, then you can read all this. I now ignore that, go back to where I was leaving here, the sync sequence. Okay. This sync sequence is quite extensive, okay, because there's a lot of variables and factors involved. But it basically talks about what absolute synchronization is. It talks about what we've got configured for the record table, the extended process data, the wiring information, so on and so forth. The next rung here, no operation. This right here, if I can zoom out a little bit here, so we get it all in view. This explains to you what my whole sequence is doing step by step. There's a number in front of it, so this 25 slave axis method sequence. If I go find step 25, that is the set gear in master position value method sequence complete. Okay, exactly like I said. So it's been labeled properly. And basically does all the work for you. So let's show you all this in action now. Okay, I'm going to download this code. So download here. Put it back in run mode. We're in run mode here. First thing we'll do is we'll come down here and make sure we have a connection and that we don't have any faults. So there's no module faults in here anywhere. Everything seems to be working. If there was a fault in any one of these, there'd be a little thing here. For example, if I pull the cable off of the slave here, you'll see here now we have the yellow problem indication here. I'll connect it back up and it will self-clear itself in a second, so everything's good. And let's just close this, and we're online here. Okay, well the first thing we need to assure is that we don't have the plug-in control active on any of the axis, because the PLC will be fighting that and not do anything. Okay, so this has to go off, this has to go off, and we can simply go to the control tab. Well, I think my favorite tab for this is this encoder interface tab on both. Okay, so right now we have some faults, but what are the faults? Process communication failed. 391. That's basically the Ethernet cable that I pulled. If I want to clear the master, for example, I go into here to the common control, and we'll see here that we have the error is active, so we have an AOI and a fault active. If I was to go look at the AOI itself, we'll see here that we have the zoom in here a little bit. We have the access error and we have the function block error. So those are the same bits, same in the one. And if I toggle this bit on, it just turned that on and it just reset the fault. You'll see here we have the green now, so on and so forth. You're getting these traces because of how the trace is set up. Every time there's a fault clear, they'll do a trace if this trace is active. So we've just reset the fault. That's a manual way of doing it. And as we can see here, we are not synchronized. And we're out by 0.1 here and 0.1 here. So it's not bad, okay? So if we go to the PLC code here, we'll see here that we're not synchronized, okay? So I'm simply going to start up my sync sequence here and my direct mode sequence. And I want to toggle this bit off, and I want to toggle the reset. The reset resets all the steps, okay? Doesn't matter what was happening in the past. Again, toggle the bit, it will reset all the steps. So if I toggle this bit on, for example, and then I come up here and I toggle the bit, it resets the whole sequence. This has to be turned off and this has to be triggered once. It'll reset itself when it's finished resetting everything, okay? And that's the prerequisite for the sync sequence, okay? If I scroll down to the top of this sync sequence, I'm going to come up here and I'm going to Control T and reset this sequence. And at this point, the way that this sequence is designed, if I enable this bit right here, it should go and execute the entire sequence and put the axis into synchronization. So I'm going to toggle this bit, and you should see this bit come on and hopefully shortly after go off. So I'm going to toggle the bit. So it's going through the sequence. It went through the sequence right to the very end, and when the sequence was over, it reset this and all the steps. Now if I go to the routine here, we can see here that the slave is geared in, okay? And we have 169.99, 169.99, and we're practically identical here, okay? So now at this point, I'm synchronized. And I can go to my direct mode sequence and I can enable the sequence to be active, and this will continuously cycle through on the master. So set point positions are changing and the axis is changing along with it. These encoder counts are happening and the slave is geared into it and it's following it as well. If I come back to my code and toggle this bit off, then the axis should all end up at 0 because that's the last step, and the routine is finished. And if I go to here, then my set point is 0 on all the axes, okay? So now I'm going to simulate a fault, okay? So if I go to the user manual, at the very end here, I have an error recovery section. So I basically talked about the fact that, you know, gear in synchronous absolute mode is considered the normal working state. So error recovery is my term for saying, okay, if we encounter a problem, how do we get back to the synchronous absolute mode, which is the normal state? And in this guide here, we've talked about 3 situations. Okay, the one situation is pretty straightforward. It's what's common at anything. It's out in the field. You have a safety relay. Could be an e-stop, could be a gate relay. That's all wired to the CMMT, and we have the motor and drive situation. SS1 stop is the norm for servos, meaning when we hit the e-stop, the control enable on the CMMT will be removed, and a program deceleration will occur. Upon the safety relay timing out, the STO signals will be removed, or the safe brake control signals will be removed, and therefore the power stage is removed. So basically the CMMT was control stopped, and then the power stage disabled, making the unit safe to work on, so forth. So in this routine here, we talk about the fact that it's working normally, and then we've lost either STO A or B, SBC A or B, or we've simply dropped the control enable, or we've lost the 24 volt DC source for the control enable. Okay, so when that happens, regardless of the fact that the physical plate or physical connection is in place, you could still have a small error difference between the master and the slave. And in order to recover from that, it's described in the manual here what you're supposed to do. Basically reset all the faults, re-enable the axis, and then at that point you only need to execute record number 1, which is the gear in synchronous absolute position. It's very simple to explain, but from a code standpoint, it's a little convoluted, which is why I've done all that in the code. And at this point, I'm going to have the axis running, and I can go up to my slave common control, for example, and if I toggle this off, I'm going to drop the enable and basically simulate a e-stop. Okay, so if I drop that and go to the axis now, the slave is not geared anymore. It's inactive down here, and we have 169.99, 169.94. They're pretty close. Okay, so at this point, to recover, I would enable the axis. So I'm back enabled here, power on, and all I have to do is toggle this bit off, toggle this so that we've reset the sequence, and then go to the sync sequence and toggle the bit. And by toggling the bit, if you read this very detailed routine here, it goes through here. It determines if the tolerance is out between encoder 1 and 2, which is X2 and X3 interfaces, compares them to the master, this one right here. And if it's out, then we have to set the master position. If it's not, we simply need to gear in, and we simply need to execute this record right here in the record table. Okay, so when I come through here and I simply toggle this bit, it'll go on, and it's been reset. We're back into gear in mode, and if I go to the encoder interface, we're geared again. 169, 169.94, 169.94 are all of them. Okay, so now let's do something a little more complicated. At that point, I could simply start the axis and it would start running again. The next one here is power supply. So this is a really good example here. Okay, So some conditions that can compromise the slave, we have disconnection of the 24 volts, which is this at top here, the 24 volts going in the controller. Or the 230 or 400 is disconnected. I don't know if that does it entirely, maybe that's a typo. But one way or another, the controller is powered off and then we power back on. At that point, we're going to see what happens here. Okay? And in order to recover, as my sequence does, the first thing it does is it looks at the tolerances and compares the master axis X2 to the master X3. It compares the slave to the slave, and then it compares the master to the slave encoder X3. If any of those tolerances are out, then we need to set a master position value using that method I described, and only after that's done do we enable the axis, and then we gear in. Okay, so I'm going to save the project because I don't know if I've saved it recently. And I'm going to simulate a power off. Okay, so I've disconnected from both. We remember there that we were around 169, and now I'm simply going to drop power to the axis. So the controllers are 100% completely turned off right now. The 120 and the 24 volts are missing, and now I'm turning everything back on. So we have a connection again, everything's back to working normal, and we'll go back online here. If I have any discrepancies, I simply do a read only. That way I don't interfere with what's happening in the drive. Okay, I'm going to go back online with this one. Like I said, I'm just going to read. Okay, so we're online again, and we'll see here that the master absolute is the same. This one here is the same. Which is very odd. I don't understand why that worked like that, because in my perspective, this should be 0 right now, but it is what it is. I can simply come through here, toggle this bit, and now the axis will be synchronized. 169.94, 169.94. Okay. Okay, well, the next error recovery is the encoder emulation cable. So if I zoom in here, what this is discussing here is the fact that at some point the cable fails. It can be the X10 to X3 coming from the master. It could be the reverse of that, slave going to the master. One of those cables or both of them have failed, and what's going to happen? Okay, so what I'm going to do is we're synchronized right now, we're geared in, and I am going to start the sequence of moving the master, then the slave will be following. So right now the axes are both moving, and I am going to disconnect the slave X3 port, and I've pulled it, And now I'm putting it back. And if I go to the diagnostics, device state, we'll see here we have an incremental encoder analysis invalid because we've lost the signal. If I go to the master, go to the diagnostics, IO state, device state, sorry. We have the position difference encoder 1 to 2. Okay? And then if I come over to the encoder interface, we'll see here that the actual position is 58 on the actual motor, but the feedback is not a match on the encoder. If I look at the slave encoder position, 64, 64, 64. So what happened there was I disconnected the X3 connector, and so I disconnected this cable right here. So basically this right here was being transmitted. Let's look at this picture here, it's a little better. The encoder position was being transmitted and emulated out of X10 to the X3. So the slave stopped following, and it stopped emulating the signal because it stopped moving because there was no more signal coming to the drive. Then, because the slave was not sending its signal out of X10 to the X3 over here, the master recognized the fact that now there's a difference of position, and it stopped the axis due to that fact. Okay, so now we need to recover, and to recover from that, my sequence takes care of it all. Again, we turn off the normal sequence, we reset the sequence for the master, then we go to the sync sequence, and the sync sequence will look at the positions, realize that they're different. It will correct everything. Okay? So if I toggle this bit, it's going to go out and it's going to resynchronize all these axes. It just miraculously changed this by writing the master offset, and it's going to move the axis into place and then synchronize it. So now we're synchronized at 5886, 5886, 5886, 5886. And it's that simple. There's a lot of code behind this, but this sequence takes care of it all, or at least the main core concept of the MasterSlave. All the fault monitoring, everything else, that's all up to the user to configure and program. I hope this video helps you guys. Enjoy your day.